Yesterday, I uploaded a video on YouTube and we realized there is no voice in that. Still some issues. Still some problems are there. I think I'll have to mute that mic again. No choice. All right, so reminders. All right, 27 terms. Similarly, if you have any fourth order or fifth order tensor, I am sure you will be able to write the expression using the dyad of that order. Yesterday, when I introduced the notation for a tensor, we just said that if I put an underbar, it means a tensor. Of which order, it will not be clear looking at the symbol itself. However, now we have a hint available by which you can infer the order of the tensor if we have expressed that tensor in Cartesian coordinate system. Suppose f is a vector. हो गया ठीक? क्या किया आपने? आपने समझ लिया? ठीक है. All right, thanks. good. So hopefully the voice will be there in the video. All right. So if I just show you this symbol f underbar, you know it is a tensor of which order not clear. But if I have also expressed that tensor in a Cartesian coordinate system like this, the expression will be vi ei hat. Okay. Since there is only one unit vector standing here, that tells us that f is a first order tensor, order vector. Similarly, if I just show you s, we don't know the order, but the moment I express that using this coordinate system, you see it is Sij, Ei, Ej, two unit vectors standing next to each other. You know it is a dyad. It means S must be a second order tensor. And similarly, for other tensors, you can infer the order. So how many unit vectors are here? That decides order of the tensor. Standing next to each other. Okay. Now, if I only see some scalar components, okay, with some indices or subscripts, what do we infer? While deriving these equations, we will come across such situations, Sij, Ei, or you will come across a quantity like Vi. Now notice in Vi, there is one index appearing, only one index appearing. When there is only one index appearing, we call that index as a free index. It's not repeated, appearing only once. And since this symbol has only one free index, you think about it in the background of what we have learned so far, you can conclude that Vi must be the ith component of a first order tensor. That is why it has a one free index. Compare this situation with that symbol Sij. So I am talking in the background of these things what I wrote here. Okay. Now, ideally, I should have written this as V. That would be consistent. Now, if you just see Sij, how many non-repeated indices? 2. We will say it has 2 free indices in our notation. And then we can also infer that since there are 2 free indices, it must be the ijth component of a second order tensor. So the number of free indices in a scalar is telling you that it is that component of a tensor of that order. Right? If you see Tijk, 3 free indices, it must be the ijkth component of a third order tensor. So either I write the expression of the scalar component, or I write the full expression. Once you start referring to a coordinate system, there are enough hints available to infer what order tensor you are dealing with. Okay? This is what I meant when I said yesterday that there will be some information available in the context to judge the order of the tensor. These are examples of such information. Moving on, now let's talk about different kinds of tensor products. Different kinds of tensor products. Again, if you go back to first order tensor, that is a vector, you are already aware of 3 types of products. 2 you were familiar even before this class, dot product, cross product, and then yesterday I introduced dyadic product. Now, if the tensor is general, not necessarily a vector, second order, third order, fourth order, there also we talk about some products. Two products we are interested in in this course, dot product and double dot product. There may be other product types of products also, but in fluid mechanics, in the study of fluid mechanics, at least up to the distance we want to travel in this course, these two types of products of higher order tensors would be good enough for us. So before I give or write the details of dot product for higher order tensor, let's review the dot product of vectors. Again, something you are very familiar with. I'm going to use the same Cartesian coordinate system as my working coordinate system. Okay. And I'm going to perform this operation dot product of vectors using this coordinate system and simplify the expression. And then we will learn something about index notation. Index notation means writing a vector like AI, EI, EJ, EJ in that way. We will learn something, we will observe something about dot product in the context of index notation, and then we will extrapolate this idea for higher order tensors. So if I ask you to do this operation A dot B in the traditional conventional way, what you were doing earlier without using index notation, you will write explicitly the two vectors in this manner. You will put a dot product here, right? And then you will expand it in this way. Right? And then you will go and take dot products of individual terms here. So you will open this parenthesis, you will take dot product of this, then this, this. So in that way, how many dot products you will take here? How many dot products will be required to simplify this? 9, right? 9 dot products you will take. All right. Now out of those 9, many will be vanishing. Why? Because this is an orthogonal coordinate system. Whenever you have E1 dotting with E2, E2 dotting with E3, those things will be gone. The only survivors will be E1, E1, E2, E2, and E3, E3. So there are going to be only 3 survivors out of 9, right? We know this. That's what I'm writing here. We know only these are surviving. They are equal to 1. And whenever I come across such dot products, I'm going to set them to 0. And if you do all that, this is the final answer you will get. Again, very familiar relationships, well known. Now what I want to do is, I want to do the same operation using what I am calling as index notation. Index notation means ij will come. Einstein's summation rule, which we made yesterday, that will also be used if required. And why do I want to do that? I said yesterday, why do I want to use Einstein's summation rule or index notation? Write less, convey more. Write less, convey more. Okay. So can we have the same conclusion with lesser number of steps? Same thing, write less, convey more, using indices. And that's what I'm calling as index notation. To be able to do this in lesser number of steps, let's define a new symbol, delta, such that delta ij is ei dot ej. I'm defining it. And again, this will go and become part of the package, what I am calling as the index notation. So we are appending index notation every day, right? As and when things are required, I add rules to this package and then I use it. So I define a new symbol. And after all, this is not completely new to you. In APL 100 also, this might have been introduced. I definitely introduced it. I guess the other half of the class was also exposed to. Yes or no? What was the context? What was the topic for it? We call it Kronecker delta. You're right. The name of the symbol is Kronecker delta. But what was the topic in APL 100, in context of which this was brought in? Inertia, inertia, inertia tensor. That's where it was brought in. All right. So delta Ij is defined in this way. Obviously, following this definition, these relationships will be true. I hope you agree. Delta 1, 1, 2, 2, 3, 3 will be unity. Other deltas got to be 0. Okay? That's what I am writing in index notation. Instead of writing so many things, we will just say delta, the Kronecker delta is defined in this way. 0 if I is not equal to j, equal to 1 if I is equal to j. Okay. Now, before I move forward, let me ask the classic question. In every class, everywhere in the world, wherever this Kronecker delta is taught, this professor, the teacher will ask you this question: what is delta II? Remember, this has now become part of the package called the index notation. So delta II क्या होगा? 1. Delta II 1. How many of you agree with this? How many of you do not agree with this? Okay. If you do not agree, what's wrong with this? 3. It will be 3. Why? Because Einstein's summation is implied. So delta II, you should first honor this rule, and according to that, it is actually this. Right? I being allowed to take its value over the full range and being added, and that becomes 3. So be careful about this. Sometimes while deriving the equation, you will end up having delta I. Don't replace it by 1, replace it by 3. So back to A dot B. Now I want to do it using index notation. I want to simplify this expression using the index notation. So I'm going to write first A as AIEI and B as BJEJ, and I will do a dot product. But before I move forward, I want to ask you, if I put AIEI, is there anything wrong if I write this also as BIEI? What do you think? I'm going to do a dot product soon, but is this a correct way to start? No? Okay, your answer is right. Your answer is right. Why? Too many eyes. अगर हमने AIEI यहाँ ले लिया है, I is the dummy index, you take another, you take I again as dummy index, 4 I हो गए. I don't have any rule to handle that. Okay, 4 क्या 3 में ही out of hand है. Problem goes out of hand even with the incidence of 3 I's. यहाँ तो 4 हो रहे हैं. You should always avoid that. Otherwise, you will not get to the right answer. So यहाँ क्या करें? You take any dummy index other than I. लिखा है. Once I is used, you should use any other index. Yes. Any other index, but not I. All right. Always follow this practice. Okay. Now let's do this dot product. So mind you, the dot product is defined. I mean, this dot will actually happen between unit vectors. So you can write AI BJ like this. In fact, if you want, you can also write this as BJ AI. Doesn't matter. Scalars है 4 times 5, 5 times 4, same ही रहेगा. What is important is this. The dot product is between EI and EJ. Okay. Now we go by the definition of delta, which I had on the previous slide. I'm going to replace it by this. While we use index notation, also keep checking that we are not violating any of the rules of the index notation, any of the rules that we have accumulated so far. Like J must be appearing not more than 2 times. Is this correct? Yes, I not appearing more than 2 times. So in that way, at least it is right. Okay. Now, once you have delta ij in your expression, do 2 things. Whenever you have delta ij while using index notation, do 2 things. Throw away delta ij, but then after throwing away delta ij, replace all the remaining j's by I, or replace all remaining I by j. I choose, suppose this. I throw away delta ij, I replace remaining I by j. What do I get? Ej, aj. Replace remaining I by j. Right? Is this the right answer of A dot B? It is. Bj aj is what? B1 A1, B2 A2, B3 A3 added. Turning out to be the right answer. My claim is these rules will work all the time. Why it works all the time, I don't have a rigorous mathematical proof. But it is, you can try to convince yourself why it is working because of this. It is working because of this. When you throw away delta ij and you only retain those terms in which remaining I is j, you are basically using all these equations in a go. You are discarding all these terms and retaining only these terms. यही हुआ है ना, यहाँ 9 टर्म्स थे, उसमें से 3 ही सर्वाइव करते हैं, और वो 3 सर्वाइवर्स हुए जब आई जे के बराबर होता है, बाकी सब वैनिश हो जाते हैं. So I do not have a better way to explain why it is working, but I know if you think about it, you will be convinced why it is working. So it is my limitation that I do not have words to express, but I have belief that if you think about it, you will be convinced why it works. Okay, so I will stop here as far as this is concerned with this now new rule, thumb rule. जहां भी डेल्टा आई जे आएगा, हम ये 2 चीजें करेंगे, you will get the answer that you are looking for. Does it save time compared to यहाँ जो किया? मतलब अगर पहली बार A dot B इंट्रोड्यूस होता, से 8th 9th क्लास और 10th क्लास, तो हम यही करते, 9 के 9 टर्म्स एक्सपैंड करते, फिर कुछ हटाते. Compared to that, now we will use this fast way. Okay, any questions? Clear? All right. Now ramp it up. We will ramp it up to higher order tensors. Come back to it. Now let's talk about dot product between 2 tensors where at least one of the tensors has an order more than or equal to 2 and the other tensor has order more than or equal to 1. Okay. We are talking about dot product between two tensors where at least one tensor has order more than or equal to 2 and the other tensor has order more than or equal to 1. Basically, I am excluding the case where both the participants are vectors. तो मैं बात कर रहा हूँ वेक्टर सेकंड ऑर्डर टेंसर वेक्टर थर्ड ऑर्डर टेंसर या कोई हायर ऑर्डर टेंसर डॉटिंग विद अनदर हायर ऑर्डर टेंसर, वो केसेस की बात अभी करें. एंड this I guess is new to you. In this situation there are two different dot products are possible. You can talk about, so suppose the two tensors are t and n. Suppose the two tensors are t and n, or let's assume the order of this is t, the order of this is n. Two different dot products are possible, t dot n and n dot t. In general, these will be different. When both are vectors, we know a dot b is b dot a. But under these circumstances, जो मैंने ऊपर heading लिखी है, लंबी सी heading, उन circumstances में, in general, these two will be different dot products. We will see. We will have an example for illustration. Also, keep in mind that when you do t dot n or n dot t, the resulting quantity will also be a tensor and it will have its order as t plus n minus 2. Again, I will not prove it in a general rigorous way, but मैं एक example लूंगा और illustrate करूंगा. And my hope is that you will see why it should be true for any order tensor. And it turns out that this thing, what I am writing here, even though I am writing under this heading, this is true even for vectors. You see, t plus n minus 2. Does it hold good for vectors? Every vector is coming with what order? 1. And resulting tensor is what? A scalar. So this rule is being followed, 1 plus 1 minus 2. So let's illustrate this dot product example, or an example of dot product with a tensor t which has order 2 and a vector, a tensor n with order 1. Working coordinate system will be the same what I have shown you. Okay. So let's first talk about t dot n. So t is of order 2, so I write it as n is of order 1, so I write it as this. This is how I start. What am I trying to do? I am trying to express this in the simplest possible manner using my Cartesian coordinate system as the working coordinate system. And after that process, I will also convince myself that yes, even in this case, t dot n will not be equal to n dot t. We will come to that point also. Again, mind you that p and q यहाँ डाला है, यहाँ पे कुछ भी ले लो, but p और q नहीं ले सकते. Same confusion will be created. Okay, let's see what happens with this. Okay. So far, whenever you saw dot product, they were just two unit vectors. And it was obvious they will dot with each other. But now you have a scenario, probably first time in your life, you're seeing there are 3 unit vectors in front of you and there is a dot product. कौन सा किसके साथ करेगा dot? We make a rule. The rule is the nearest unit vectors are supposed to dot. That is the meaning of dot product. Or I can say this is the definition of dot product. For vectors जरूरत नहीं पड़ी थी ऐसा रूल बताने की, but टेंसर जब आप जनरल बन गए तो ये रूल एक्सप्लिसिटली बोलने की जरूरत है, ये दोनों को डॉट करना है. There is no choice. ये इसके साथ नहीं करेगा. Yes. There is no derivation. I mean, तुम रूल्स की बात कर रहे हो, रूल्स बना रहा हूं मैं, आई एम मेकिंग द रूल्स, डिफाइन कर रहे हैं, मतलब इसके पीछे और कुछ नहीं है, यहीं से स्टार्ट हुआ है। हाँ, यू थिंक अबाउट इट, जब डॉट प्रोडक्ट किसी ने बताया था तो एक दो फिजिकल एग्जांपल्स दे दिए होंगे वर्क डन वगैरह के, ठीक है, लेकिन इफ यू थिंक अबाउट इट, डॉट प्रोडक्ट इज अ मैथमेटिकल थिंग, राइट? कोई भी दो वेक्टर्स डॉट कर सकते हैं, तो वो हमें कैसे पता चलेगा कैसे डॉट किए करेगा वो? कुछ रूल बनाया था, सोर्स में रूल था, हम फिर से वहीं पे खड़े हैं, क्योंकि अब हायर ऑर्डर टेंसेस है तो मैं रूल्स बना रहा हूँ, कोई डेरिवेशन नहीं है इसका, इसके बाद डेरिवेशन होता है, ठीक है? Pretty handy. Definition of chronicle delta. Pretty handy. What do I do? Rules, thumb rules बना लिया हमने, दो चीजें करूंगा, throw away delta qs, replace all remaining q by s or all remaining s by q, कुछ भी चुन लो वहां पे. I am going to write what I have in my notes. tpq ns tps, sorry, q को ns से replace कर दिया, tps ns ep. Two questions here I want to ask, मतलब kind of side menu है, जाना कहीं और है, बट दो क्वेश्चन मैं पूछना चाहता हूँ जस्ट टू डेवलप, इंश्योर दैट यू आर गेटिंग इनसाइट आल्सो. पहला क्वेश्चन मेरा ये है, हाउ मेनी टर्म्स आर इनसाइड इट? इट इज अ सम ऑफ सेवरल टर्म्स, कितने टर्म्स हैं उसमें? हाउ डू यू डिसाइड? वी हैव सीन समथिंग ऑलरेडी, बट अब मैं उसको थोड़ा जनरलाइज करूंगा. द नंबर ऑफ टर्म्स हियर इज 3 raised to the power number of dummy indices. Number of dummy indices. Remember, एक डमी इंडेक्स मतलब क्या, एक इंडेक्स दो बार आ रहा है, इसका मतलब एक समेशन है. एक दूसरा इंडेक्स आया, वो भी रिपीट हो रहा है, इसका मतलब एक और समेशन है. तो इन टोटल डबल समेशन है. डबल समेशन में कितने टर्म्स होंगे? 9 टर्म्स होंगे. So the number of terms inside is 3 raised to the power number of repeated indices. Total number of terms in this summation. Which in this case is 3 raised to the power 2, 9 terms. और ये 2 क्यों आ रहा है? 2 आ रहा है क्योंकि फर्स्ट रिपीटेड इंडेक्स p है, दूसरा रिपीटेड इंडेक्स second repeated index. Mind you, this fact, how many terms are inside it, has nothing to do with the order of tensor we are dealing with. इसके पहले मैंने जितने एग्जांपल्स दिखाए थे उसमें नंबर ऑफ रिपीटेड इंडेक्स was the same as the order of the tensor, क्योंकि उस समय मैं सिर्फ टेंसर का एक्सप्रेशन लिख रहा था, v equals viei, t equals tij eij. इस एग्जांपल में दोनों चीजें अलग हो गई. नंबर ऑफ रिपीटेड इंडेक्स दो है तो 9 टर्म्स हैं. व्हाट इज द ऑर्डर ऑफ द टेंसर? 1. हाउ डू यू नो दैट? कुछ ऐड नहीं, वेल उससे ऑब्वियस आंसर है, क्यों है फर्स्ट ऑर्डर टेंसर? तुम्हारा आंसर सही है और तुम शायद सही कह भी रहे हो और सोच रहे हो, लेकिन उसको सिंपलर वर्ड में एक्सप्रेस कर सकते हैं. वेक्टर एक ही है, दैट इज द रीजन यू सी ओनली ईपी इज देयर. सिर्फ ईपी है तो इसका मतलब है ये फर्स्ट ऑर्डर टेंसर होना ही होना है. इसको गो बैक हियर, लिखा था ना कहीं मैंने ये एक टेंसर मतलब वेक्टर, डायड मतलब सेकंड ऑर्डर एंड सो ऑन. तो यहाँ वहां एक ही वेक्टर है, तो वो वहां एक ही वेक्टर स्टैंड कर रहा है, यानी ओवरऑल क्वांटिटी एक वेक्टर है. यहाँ क्या हो रहा था, सिर्फ वी आई लिख रहे थे हम, बट वो वी आई वहां पे कुछ और हो गया, टी और एन के टर्म्स में आ गया. ठीक है, but that's a different thing. That doesn't change the order of the tensor. I hope all of you are following. If not, to feel free to ask. ठीक है, तो ये मेरा पहला क्वेश्चन था. दूसरा क्वेश्चन है order of tensor is 1 decided by this. Okay, so this is as simplified as it can be. अब इससे ज़्यादा और simplify अभी कुछ नहीं हो सकता है. We don't have any other information. I am going to leave it like this. TPS NSEP. Yes, so what you were saying कि नौ टर्म है उसमें तीन तीन का ग्रुप बन जाएगा, तुम यही कह रहे थे, वो सही है. बट इसको इन्फर करने के लिए वहां तक भी नहीं सोचना है. बस देख लो कितने यूनिट वेक्टर हैं, उसी से वो क्लियर हो जाता है. ठीक है, अब इस पे आते हैं. n डॉट टी. लेट्स सिंप्लीफाई दिस. n डॉट टी आई विल Is it legitimate way to start? पहला डमी इंडेक्स आई चुना, दूसरा आई को छोड़कर कुछ भी चुन लिया, मैंने एल चुन लिया, तीसरा आई और एल को छोड़ के कुछ भी चुन लिया, क्यू को चुना. What do I get here? Please check. I might have made a mistake, and I think I have explained enough for you to judge me now as far as algebra is concerned. I do make mistakes very often. So, कोई गलती है तो बता दो. Is it fine? सारे इंडेक्स ठीक है? Okay. So n dot t ये हो गया. So both the expressions are as simplified as they can be. So पहला part मैंने कर दिया, दोनों को अपने कार्टेशियन कोऑर्डिनेट सिस्टम में एक्सप्रेस कर दिया. सेकंड क्वेश्चन है, are they same or not? How do I judge? Looks quite complicated. इंडेक्स काफी कुछ है, डमी इंडेक्स. Also जो चॉइस मेरा डमी इंडेक्स का वहां है वो यहाँ से डिफरेंट था, तो they look very different. But that is not the way to judge. You will have to be more careful to judge whether they are equal or not. Okay, I'll do that. Yeah, more methodical way. How do we check two tensors are same or not? For the two tensors in hand, दोनों हाथ में एक एक टेंसर है. For those two tensors to be the same, पहली चीज तो होनी चाहिए उनका ऑर्डर सेम होना चाहिए. I hope you will agree. कभी भी एक वेक्टर को हम किसी हायर ऑर्डर टेंसर से इक्वेट नहीं कर सकते हैं, राइट? So they have to be the same order tensor. That is a prerequisite. जो यहाँ हो रहा है. This is also a vector. This is also a vector. Now that we know both are vectors, we can go ahead and see whether they are the same vectors or not. Now, if you have a tensor, if you have two tensors, for them to be the same, each scalar component on the LHS should be the same as the corresponding scalar component of the RHS. component wise matching होगी तभी वो दोनों tensors same होंगे. And you are familiar with this idea. Let's go back to vectors. If I give you two vectors A and B, and then I ask you what are the condition or what is oblique are the conditions when A will be equal to B. Your working coordinate system is Cartesian coordinate system. These three will be the condition, right? All three have to be followed. A1 equals B1, A2 equals B2, A3 equals B3. Then only you will conclude that the two vectors are same. Am I right or not? तीनों components same होंगे. यही चीज किसी भी हायर ऑर्डर टेंसर के लिए. अगर थर्ड ऑर्डर टेंसर है तो 27 इक्वेशंस सेटिस्फाई होंगे तभी दोनों थर्ड ऑर्डर टेंसर बराबर होंगे. ऑलराइट. Now coming back to vectors, if two vectors have to be the same, this is what should be followed. Again, I will invoke index notation, and instead of writing these three individually, I will say that this condition should be followed. AI equals BI. जहां I 1, 2 और 3 full range लेगा अलग अलग equation में. In different equations it will take the values 1, 2 and 3. So AI equals BI. In it has one free index on the left hand side, one free index on the right hand side. Both free indices are the same, and this in index notation represents apparently a single equation, but this represents set of three equations. So instead of writing these three equations every time for a vector, I will say that the condition under which the two vectors will be the same is AI equals BI. All right. Now come to T dot N equals N dot T. Are they same or not? I already know they are both are vectors. Check if the coefficient of EP in Tn is equal to coefficient of EP in Nt or not. That is the thing we need to check. Coefficient of EP in T dot N, whether it is equal to coefficient of EP in N dot T or not. If you can show they are same, this is like proving this. And that is good enough for you to conclude that the two vectors themselves must be the same. All right. Do you follow? Yeah. So let us extract the coefficient of EP, coefficient of EP or EP hat. Hat मैं बार बार नहीं बोलता हूँ, but hat is implied. EP hat, coefficient of EP hat in T dot N. T dot N का expression जो था, that is what the expression we got. What is the coefficient of EP? TPSNS, right? You can also call that as the pth component of T dot N in your working coordinate system. Also notice that TPSNS is a sum of three terms, like what I have shown there, because P is a repeated index. You can call P here a free index. In the scalar component, P is a free index. It is appearing only once. TPSNS on its own has three terms, sum of three terms, which is in line with what I wrote earlier. It is the number of terms here will be number of terms here will be number of terms in the summation will be 3 raised to the power 1, because there is only one repeated index S here. Okay, so I keep this in reserve here, and now I want to see what is the coefficient of EP in N dot T. Coefficient of EP in N dot T. Previous slide, when I simplified the expression for N dot T, this is what I got. There is no EP in that. And there is no EP because I didn't choose P to be any index when I started simplifying that expression, which is absolutely fine. So मेरा expression गलत नहीं हो जाता है. लेकिन अभी मुझे coefficient of EP की जरूरत है. EP यहाँ दिख नहीं रहा है, क्या करें? Sorry? Very good. Yes. Q को let's change Q to P consistently. Everywhere. right? Now I have EP. Now what is the coefficient of EP? NL TLP. So I'm moving closer to comparing the coefficient of EP on this side and coefficient of EP on other side. But there is still a problem. प्रॉब्लम ये है कि यहाँ पे एन एल है एक फ्री रिपीटेड इंडेक्स नॉट फ्री यहाँ भी पी है, रिपीटेड इंडेक्स एल है, बट ऑन द अदर एक्सप्रेशन फ्री इंडेक्स पी है, रिपीटेड इंडेक्स एस है. अब क्या करें? एल को एस में बदल दें. और अगर यू हैव अंडरस्टूड थिंग्स अप टू अ गुड एक्सटेंट, यू डोंट इवन हैव टू change S to L. I mean, it's implied कि LL और SS का same meaning है. But for to make it visually even more convincing, let's change L to S. Okay. So T dot N coefficient of EP in T dot N was NSTPS. ठीक है, remember NSTPS, और coefficient of EP in N dot T is जो यहाँ लाया हमने, that is NSTSP. Now tell me what's your judgment. Are they same or are they different? Not the same. All of you agree? Who doesn't agree? And if you don't agree, give me the reason why you don't agree. All of you agree. Right. In general, these two are not the same. Thus, T dot N not equal to N dot T. Simple example से हमने illustrate कर दिया. Give me a condition under which they will be same. I'll come to you. Either या and. ठीक है, वो भी covered है. I think what you are talking about is in general TPS अगर TSP के बराबर होगा in general for all PNS, तब ये दोनों बराबर. That takes us back to a definition you already know, symmetric tensor. उस केस में in general दोनों different है. Yes, you have a question. हाँ, अच्छा यही बोल रहे. ठीक है. Okay. अच्छा, एक चीज और मैं बोलना भूल गया. What is the order of tensor T dot N? हम देख चुके हैं, ये 1 है और ये भी 1 है. Is that consistent with my claim that the resulting tensor, when you take a dot product between two tensors, is going to be of order T plus N minus 2? ये consistent है या नहीं है? T 2 था, N 1 था, 2 plus 1 3, minus 2 1. Now you visualize why it is happening. Can you explain? Can anybody explain to me? ये formula तो मैंने ऐसे ही फेंक दिया. I threw it at you, and I'm showing that कि मेरे examples में सही है. Can you visualize why it is happening? बच गया था, वो भी एक तरीका है देखने का, बट उससे ज्यादा ऑब्वियस मुझे जो लगता है वो ये है कि एक डॉट प्रोडक्ट में 2 यूनिट वेक्टर सैक्रिफाइस हो जाते हैं. थिंक अबाउट इट. एक डॉट प्रोडक्ट मतलब 2 यूनिट वेक्टर सैक्रिफाइस होके एक स्केलर बन जाते हैं. वहीं पे 2 ऑर्डर स्लैश हो जाता है. दैट इज व्हाट इज अपीयरिंग हियर एज ठीक है, और ये प्लस क्यों हो रहा है, क्योंकि ये डायडिक प्रोडक्ट बन रहा है, साथ में आ रहे हैं। बाकी के यूनिट वेक्टर्स दे कम एंड स्टैंड नेक्स्ट टू ईच अदर, तो वो t प्लस n हो जाता है और दो सैक्रिफाइस हो जाते हैं फॉर वन डॉट प्रोडक्ट. So that's the kind of visualization of that. I'll take 2 minutes more and then I'll let you go. Double dot product. First idea. Planning is okay. Now let's talk about double dot product. Let's start talking about double dot product. Now double dot product is defined for two tensors where both tensors have to be of order more than or equal to 2. तभी डबल डॉट प्रोडक्ट डिफाइन होगा, एंड इट विल बिकम क्लियर व्हेन आई गिव द डेफिनेशन कि क्यों इसके लिए दोनों पार्टिसिपेटिंग टेंसर्स को कम से कम सेकंड ऑर्डर टेंसर होना जरूरी है. I'll show that. Another, again I am claiming, resulting tensor after a double dot product will be a tensor of order t plus n minus 4. Can you visualize why it will happen? क्योंकि यहाँ दो डॉट प्रोडक्ट होने वाले. Okay, we will make some rules कि पहले कौन होगा बाद में कौन होगा, but eventually at the end of the day there will be two dot products and every dot product sacrifices two unit vectors. So eventually चार unit vector sacrifice होने वाले हैं, and that is why it will be t plus n minus 4. In general, again, t double dot n will not be equal to n double dot t. Order matters in general. There may be some special cases जिसमें ये true होगा, in general नहीं होगा. I will illustrate this with an example when both are second order tensors. Both are second order tensors. I want to leave you with the one thought. You may be wondering why this specific ways of why we are defining dot vectors, dot products in these specific ways. I'm going to tell you that